All right, everyone, this is our last video that is associated with the equilibrium part 1 PowerPoint presentation. So this is slide 6 on equilibrium part 1. The PowerPoint is linked in the module. It's a little bit higher up probably than this video. Okay, and this last slide is we can convert between K in terms of the partial pressures and K in terms of concentration. Now this confuses students because we set them up the same, right? It's products of reactants. Solids and liquids are just a 1, or we sort of exclude them altogether in a way. And the coefficients are the exponents. It's set up the same way, except it's in terms of pressure versus concentration. Well, the number for partial pressure is not the same as the number for concentration. 1 atmosphere of partial pressure is not necessarily 1 molar of concentration. So the numerical values of Kp and Kc are usually different. Okay, so Kc is just concentration in terms of molarity, and Kp is the one we set up in terms of partial pressure of each reactant and product gas. So here's how they're related. Fun fact, the ideal gas law, if you divide both sides by volume, you get pressure equals N over V times RT. Well, that is molarity. Pressure equals molarity times R times T. Okay, so let's go back to K in terms of, right, if we have Kp, this is Kc. Molarity is our concentration. So the relationship between Kp and Kc, there's a little twist right here, delta N. So we're going to practice what is delta N. Delta N is the number of moles of gas on the product side minus the total number of moles of gas on the reactant side. Capital P for product, capital R for reactant. So we'll have to do 2 steps, at least for this problem. The first is we'll have to look at the reaction. We have to have the reaction because we need to know how the moles of gas are changing. And the other thing is we'll need some of these numbers to work with. Okay, so let's look at our example here in the slide. I'm going to rewrite this equation. I've got 2 nitrogen monoxide as our formal naming system, plus dioxygen gas in equilibrium with 2 moles nitrogen dioxide gas. All right, fun fact, one of these is laughing gas. All right, so what is delta N? Let's look at how many gases, moles of gas. So I'm looking first for what has the letter G, the phase after it, and then I'm looking at the coefficient. I only have 1 product, and it's a gas, and it's 2 moles. It's 2 moles of gas minus, I've got 1, 2, 3. I actually have 3 moles of gas on my reactant side. That's a gas, that's an understood 1, that's a gas, and that's a 2. So 2 plus 1 is 3. You have to add up all the terms that are in the gas phase on both sides of the arrow and then subtract the reactant moles of gas from the product moles of gas. Okay, so this one, 2 minus 3 is -1. So what that looks like is Kp equals Kc times RT to the -1, or 1 over, right? A negative exponent means that's in the denominator. So another way to write that is Kc over RT. The delta N only affects the RT term. That's why we have parentheses around it. It does not affect the Kc value. So that's the equation when delta N equals -1. Okay, So now we have a value in the problem. If Kc equals 2.95, what's Kp? I'm going to use temperature 298. That wasn't given in the problem, so I wouldn't be able to solve it. But typically, they're either at 0 degrees C or 25 degrees C. I'm going to use, just for us to finish out this example, I'm going to add in that piece of information. Okay, and then R is 0.0821 liter atmosphere per mole Kelvin. That's R, the gas constant. Okay, so now I'm going to plug in these numbers. Kp is what I'm solving for. 2.95 and then 0.0821. Sorry guys, that hood just decided to go off. Low pressure alert. I know this needs to be in Kelvin because that's the unit of temperature in my constant. Okay, so I'm gonna turn off that and then plug that into your calculator. Okay. All right, I'm gonna pop on over to the scientific calculator that I was using earlier, and I'm going to plug in 2.95 divided by, and I'm going to use my parentheses because order of operations will totally mess me up, 0.0821 times 298, close parentheses, equals 0.121. If I want to round up a little bit. All right, let me go back. I wrote that on our screen. And these are unitless, so this is not in atmospheres. And the Kc is not in molarity. They don't actually have a unit associated with it at all. Okay, so that should set you up. I do want to say one problem that I really love to ask is, when is Kp equal to Kc? I'll talk about that just really quickly. When is Kp equal to Kc? I love to ask this question. If we write the equation, when are those equal? Well, if that term is a 1, if R times T is actually equal to 1, what exponent always gives you a value of 1? 0. 500 to the 0 power is just 1. 2 to the 0 power is just 1. So if the difference in moles of gas is 0, if it's an equal amount of moles of gas on both sides of the reaction, that means this term is a 1, which means Kp and Kc are equal. All right, just a little nugget to help you prepare for your exam.